On these four generic examples, we'll remind how to calculate limits of functions in given points using basic knowledge about limits of number sequences. To do so, we'll use the Heine definition. So accordingly, in the first exercise, we tend to number 2 on arguments of a function that has formula like that. So according to definition, we can take basically any number sequence that has a limit 2. But of course, for no n, it cannot be exactly 2. So it's not possible for any of these elements of the sequence. And of course, all the numbers in our sequence should be actually members of domain of this function. But this time it shouldn't be any problem since domain of this function is basically anything. There is no need to remove any values from this set. So let's swap into that. So this time we have the usual limit of number sequence. And there we simply put its general element inside here. So very similar look. But of course now, since it's just a limit of number sequence, we can use anything we know about them. And especially since we know that this is a convergent one, we can simply separate these calculations according to linearity of it, leading us to having 3 times our limit that we actually know. But first I'll just rewrite for simplicity, but of course squared. So here square. And this part separately as a sequence is simply a constant one. So its limit is this -2 number. We can rewrite it. So since we know it's 2, the calculation becomes very basic. So we simply have 3 times 2 squared minus 2. So 12 minus 2, leading to the answer 10. But note that actually our point in which we were calculating the limit was actually a member of the domain. Next, we have a bit different situation because see that -4, the number in which we want to calculate the limit, basically must be excluded from the domain, since then there would be a division by 0. So this time, domain of our function excludes some points, in this case -4. But still we can use the same easy approach. So we'll take any sequence that converges to -4. And of course, all these members of the sequence cannot be -4, which is now quite obvious since it's outside of the domain, must be from the domain, but basically all numbers are except -4. So we can simply rewrite it just like before, but before I will do it, let's notice that actually we can do here some simplification. Since we do have a square of some number here and square of some number, namely 4 or -4 there, we can use the school formula to obtain the same value in a product in the numerator as in the denominator, which will help us a lot. So let's see it. So rewriting as the usual limit, but I will already do this simplification, so I will write it down as xn minus 4 times xn plus 4 instead of xn squared minus 16. To notice that this is basically same stuff as here. Now focus on this part since it repeats. Basically, it equals 1 because we have the very same value above and below, except for -4. But since it's already excluded here and there will be no problem out of it, and we can actually simplify already. So skipping this, being just 1, will lead us to the situation when we do have our known limit, and basically minus limit of constant sequence being equal 4 all the time. So basically we can just rewrite -4 just like on number sequences, no need to do it more times. So using our knowledge what this limit is, it's basically our assumption we have -4 being -8. So also often situation, even though this x is excluded from the domain of this function, it actually does have a limit in this point. Now, we can of course always stick to this moment and just use Heine definition and only calculate number sequences limits. But since most elementary functions, we do know their limits in most cases, and some properties between them you can find listed in PDF files, in many cases we will skip this, moving into having a number sequence and just stick to calculating limit of function when it's readable. And of course we can use all the properties we know also for number sequences, since they're translate easily into the function ones. You can also check it out in the PDF file. So now in the third situation, we'll see easily, before even going into the number sequence, we'll see that we can separate it into two parts, like sequence of function x and sequence of this sine function. And you can easily notice that we have the situation on one of the basic lemmas about calculating limits. Obviously, as x approaches 0, since it's the whole function here. And see there that whatever we have inside, sine is never smaller than -1 and never larger than 1, so it's bounded. So we do have a situation of limit that converges to 0 times some bounded sequence or bounded function like here. So according to this lemma, each time it happens, it's 0. And finally, let's move on to the last one. Notice that we have sine of 3x's, so it alone, as x tends to 0, converges to 0, but unfortunately the same happens there, since tangent of 0 is 0 as well. So we do have something called indeterminate form, basically 0 over 0 type. As you'll learn later derivatives, there will be an option to solve such examples using the so-called de L'Hopital rule. You can check it out in the later videos, but it will not work always, but in most our situations, and especially it's not actually mandatory. We can easily solve this example, just like we would do this for the similar number sequence, or just using the formulas you have listed in the PDF. So we do know that sine and cosine functions actually converge to their values in any point, but it not necessarily will be useful there alone. Since the limit is in 0, probably we will try to use one of the known limits that include it, namely very often used one, like that you should remember after learning about limits of number sequences. And as you hopefully remember, or just check it out in the PDF file, it's equal exactly 1. So let's try to get it here. Probably we'll use the fact that tangent is sine over cosine in any point wherever possible, so probably will be useful. Let's do so. So we still have limit in 0. No need to touch this sine yet, but it's over sine of 5x over cosine of 5x. But to not have two division lines, maybe let's write it down as not divide by multiply by cosine of 5x over sine of 5x. And since we do not have sine x but 3x or 5x, we need to have here 3 5x, so also there. So they will converge to 0 at the same pace. So let's simply create it. So we have this limit. We need our sine to be divided by 3x, but since it wasn't there, we need to multiply by it once more. There is no problem with our cosine, since cosine of 0 is 1, so we can simply put it here. But we need the same trick with sine once more. So we want it to be over 5x, but since it wasn't there, we need to multiply by it once more. Remember that as we converge to 0 on arguments, it simply means that we do not consider x equals 0 at all. So we simply can simplify it here. We will take into account that this one tends to 1 and this one as well. From this known formula you can easily find in the PDF file. Here we have number 3, here we have number 5. And moreover, cosine of 5x as x gets closer to 0 tends to the value cosine of 0 being 1. So that's basically solved. We do have 1 times 3 times 1 over 1 times 5, over all leading to the result 3 over 5.